Hey there, Bushy here. Today I'm building a climatized breeding box. A what? A climatizer breeding box that accommodates a jam jar and keeps it at a specific temperature. That is slightly higher than room temperature, around about 28-29 degrees centigrade. And why I need this and for what it is useful, we will come to in a bit. But for now, it is enough to say that we need it for our täglich Brot. If I have a jam jar like this, or that was made for honey or marmalade, or jam actually, jam jar, right, makes sense. I thought about something like this footprint for the electronic parts, then this comes on top, and for isolation to keep it at like specific temperature, a cover so that the air is not, there's no convection, there's no air circulating, etc. And as I'm a pretty careful guy, at least that is how I would describe myself, I didn't want to have PLA, which is the only plastic that I can currently print. I wanted to have some sort of metal base where the jam jar can sit on, and also the heat is then spread more evenly, and that is why I bought an aluminum sheet like this. If you have been following the channel, you know that I'm a big fan of ESPHome, simply because it is so simple to get an electronic project going in no time by leveraging building blocks that click together, configured by YAML files. Really, it cannot get any simpler. There are no stupid coding errors that I myself introduce and then need to chase for hours and hours. I don't have to come up with a good program design for the embedded chip. And then something for something that I just want to have and use in my home. And not even starting to talk about the native Home Assistant support, to then have it represented where all my appliances in my home are represented. It feels natural. Okay, enough of the pep talk. Back to the meat. What do I need for this project? I want to heat these type of jam jars. I think this one was for marmalade or honey or alike. I need to some sort of heater, obviously. For example, a foil heater. I need a temperature sensor that tells me what temperature this thing and the enclosure currently has. I need a switch to heat, to switch the heating element on and off. Some sort of strong enough power supply, of course, to drive a heater and the ESP module. And then finally, some sort of ESP chip. Initially, I wasn't sure if ESPHome can support me with all those things to integrate into one project. Or rather, I should say, I was not so much questioning if all the different building blocks are there available, but rather if I can dig them out in a reasonable amount of time and make them work together. And to be honest, it was a no-brainer, really. Let's jump over into the code and I can show you what I mean. So this is now the code for this project, and I will completely gloss over all the boilerplate that is happening in the beginning, because that is repeating every single time and there's nothing new and there's nothing fancy. So let's gloss over it and come directly to the bottom of this program and start from bottom up. This one is the simplest one, I would say. It's a number template, which gives me the ability to control a number from from Home Assistant and dictate it into ESPHome, which I can then use it in as a variable, which is the temperature that I want it to target. Okay, it's a very complicated way of saying this is a means to control the target temperature of this appliance. And whenever there is a set action coming from Home Assistant, then the climate control module, which we will look at in a second, is getting or is given a new target temperature. All right, next one in the line is the output module. I have this heater element on this metal plate, and obviously I need to heat it up quite a bit, and there will be quite some amount of amps flowing through this. So driving this with a normal ESP pin is completely out of the question, obviously. So what I need is instead some sort of switch, a bipolar transistor, or a MOSFET. And I choose a MOSFET, spoiler, and drive it through this module in a very low PWM fashion with a very low frequency, because that is more than enough. This is handling then the output. It's given a pin that is the control pin for the MOSFET of this is driving me crazy how this is popping up all the time. The pin on the ESP driving the MOSFET, and then this is controlled by what we will see in a second. Next one is the sensor, which I have shown you here. It's a simple, very simple DHT22 model, a very cheap one, very nicely available one, not overly precise, but to be honest, the precision is not really needed for this project. I give the different temperature and humidity parameters some names here and an update interval of 5 seconds, which is more than enough because the temperature transient that I will be reaching, the gradient that this can achieve, will be really, really slow. And last but not least, we come to the last module in this project, which is actually the most important one, which is this one. It is of the type PID, which stands for, it's a controller type, stands for Proportional Integral Derivative Control Approach, which is defined by 3 different parameters, those 3. In short, this one dictates how much control output is generated with a specific offset between the sensed value and the target value. Integral makes sure that if there is an offset, it will not stay like this forever, but it will be decreased and creep towards the final target value. And then the D is the derivative, which is a counterbalance to the integral part, so that even though it is creeping toward the final value, it is not overshooting it and then maybe even going into an oscillation or going out of control completely. I haven't really touched those values here. You can see that there are 2 more things defined here. Some sampling is going on for the control. This is driving me crazy. That is always popping up and overlaying where I'm currently looking at. And then as a final thing, there's a dead band parameter. So whenever it's in 1 degree centigrade, in the reach of the target value, there's no control output anymore generated. If we jump over to the description on ESPHome for this, you maybe realize that those values that you have just seen look familiar because I haven't even touched them. And I think it's also not really necessary because this entire thing is fairly slow because there's quite a significant of metal here. And the heater foil that I'm using is actually only 2.5 watts, so fairly small. I did some rough calculations using the enclosure that I was designing or that I designed, the thickness of it, the material, the surface of it, to estimate or guesstimate, I would say, if I'm at all able to bring the inside temperature to a significant different value compared to the outside temperature. Depending on the material constants that I was searching on the internet for PLA, it was between, or it was below 1 degree that I could change up to 5 or 6 degrees, depending on different values for PLA and how well it isolates temperature-wise or temperature energy flow-wise. And I wasn't sure. So, I mean, this is relatively easy to be fixed with a different heater element, obviously. I wanted to have this as small and non-dangerous as possible, so that this entire thing that I'm building here is not lighting my apartment on fire or lighting it up in flames in the end. That is also why I have this metal base here and then have it separated from the holding bases that I designed here, which is then sliding into here and fixed by screws from the bottom, which is then holding the electronics, which I have here. It's a small PCB Lochrasterplatine. Whatever this is in English, I have no idea. And I was using one of the leftover ESP modules that I was using for one of the recent projects with a USB-C port, which is very convenient because everything is more and more USB-C these days, and it is great because it's a nice plug. I have a MOSFET here that is an IRL Z44N, which is a logic level driven MOSFET. And then finally, last but not least, power circuitry, which is something that I haven't used until now, but I was recommended it like a long time ago. It is also USB-C, and you can plug one of the more modern USB-C power delivery plugs that have not just 5 volts as in the good old days, but are able to provide different voltages. This one, for example, can provide 5 volt, 9 volt, 15 volts, up to 20 volts. And then at 20 volts, it can provide 1.5 amps, which is roughly 30 watts. So quite an amount. And then this board is only making sure to communicate via the USB protocol with this thing, telling it how much volt I actually want. And for this project, obviously I want 5 volts because that's the simplest I can choose. I also made sure that this heater element is 5 volts compliant. I could probably also drive it with higher volts, but then it would get warmer. And I'm not sure if it's designed this way, so I stayed within the specified limits for this one. So 5 volts, 2.4 watts, switched by a MOSFET, which is completely going overboard with its size. It can support much higher currents if I want to. And if this is not heating up enough, I can just buy a different heater element or put more heater elements, although here it would be kind of difficult. And bring more power into it and give it more force so that the control algorithm can actually do a better job. I would say, let's go down and put it all together and then test if it actually works. So while the construction is ongoing, let me explain why we actually need this temperature climatizer box and where the origin of this idea came from. My wife likes to bake cookies and cakes, but also delicious bread. And for some time now, we discovered sourdough bread for us, and it tastes really good, and it's a nice dark bread and really cool, and you can make it yourself and everything is fine and dandy. In case you're not so familiar with these kind of doughs, the basis is just flour and water, and then it has something to do with lactic acid bacteria and yeasts, which you need to pamper in the right way and feed from time to time with more water and flour to get it growing and healthy. This is then the basis, or this core dough is the basis partially used in the production process of an entire bread, while the remaining part is left over and you can keep it and feed again and grow further for subsequent breads. I really don't get the magic about the different classes of doughs. She's pampering day in and day out, so better don't ask me about it. It really looks complicated, and apparently it is. Recently, we noticed a slight decline in final bread quality, leading to denser and not so fluffy breads that also didn't taste as good. My wife mentioned that fluctuations in temperature or humidity in the kitchen now that we have wintertime might be behind this decline in quality, where the dough is just not so happy anymore and comfy, and that she probably needs some sort of climatized box or environment to keep the temperature more steady and more consistent. And then we quickly checked whether this is something you can buy off the shelf, and in fact you can. But I mean, come on. The moment that I thought about the entire problem and how to solve it, it clicked for me, and I decided that this is a project that I need to do myself. And if you think about it, there is no need to buy something off the shelf if you can build it yourself. And in the end, it only costs double the amount of the original product and takes a couple of weeks to put together. So perfect. And here we are and here we go. And that is the backstory for why I wanted to do this myself. And actually, yeah, it turned out to be great. But let's continue now with the build and the testing phase. I have to say, I really like the idea that I came up with in the end, where all the electronics and the metal base all belongs to the same component in the end, and then is only inserted from the top onto the bottom case. Makes it really easy and simple to take it out completely in its entirety for service or changing stuff. So now is 2 days after the last recording, and the Sour Tiger box had time to get comfy and accommodate itself, and I had time to play a bit with this, try to and reach the limits, try to see where the limits are. So pumped it to 40 degrees target value and see how far up it can go, and then put it to a more lower value where we actually want to operate it and see how steady it can keep the temperature, even though there's maybe offset going on, or is it like if it's going to put it on a steady temperature, or if it is like shifted to whatever. So yeah, and then also in the meantime, my wife was waiting for this to finish finally, and put already some dough into one of her glasses and let it breathe. So this is how this looks like. Not too nice, but I see some bubbles, so that's good. So this is eating the flour, I guess. I can also see condensation water, which is good because it's there seems to be some heat in there that needs to go out. So that is actually quite good. Maybe let's look at the graphs and see how well it performed over the last 2 days. Yeah, so this is now the representation in Home Assistant. That is my page for this project. You can see Sour Tiger here. And this is actually the temperature of the kitchen, which was not fluctuating too much. So going down during the night and then going up during the day, more or less 1 degree. But as you can see, this fluctuation is visible inside of the Sour Tiger temperature box. So this was now with a target value of 40 degrees, and this is what it was able to achieve with that. So, and if we now look at this graph and this graph here at the bottom, we can then determine how much temperature offset it can achieve for a certain environmental temperature that is happening outside. So maybe let's look at this. So here the maximum was at 11:30, 22, let's say. And they stopped. Okay, then we should look at 10 a.m. At 10 a.m. it was 32. And here 32, and we have like 20, 21, 22. So that's an offset of roughly 10 degrees that it can offset the current environmental temperature and produce a high temperature inside of the box, which means that if I put it to a lower temperature, somewhere in that span, it should be able to operate the heating element in such a way that it keeps this steady. And if it drops then a bit, the environmental temperature drops a bit, there's still enough room, like head lift, to put it and keep it at this temperature. And if it's going up, there's less that we need to do. In the summertime, of course, if it's getting much, much warmer, there's only so much that we can do. And once it reaches this temperature, it will like take it up with it because I have no cooling, no active cooling. Although, I wasn't thinking about this, but yeah, maybe a, what's it called? Peltier element. I need to look, anyway. So that might be an option. All right. And then after it reached this point at 10:50, I set it to a lower temperature, which was 27 degrees centigrade, and wanted to find out how well it can put it to this temperature and keep it at this temperature. And as you can see, there was some oscillation happening there. Let's go to the graph. So we want a time between 11 onwards today. Yeah, something like this. And it was oscillating then back and forth, plus minus 1 degree. So the total temperature oscillation were around 2 degrees. around the target temperature. And at first I was a little bit confused about this and thought that this is due to the that value range of the PID controller, which I set maybe to 1 degree plus minus, and only once it exceeded this range, it started to operate the controller, but that was not the case. And then a second guess was that during a phase where it was overshooting, for example, it accumulated integral compensation, and that compensation was growing and growing and growing, or actually in a negative direction when it like overshot. And that was just going too big. And once it reached the crossing point, it was maybe reducing that due to the derivative component, but not enough. And then overshot it. And then only then it was finally, deleting and removing this integral part. And then it was already too late and it overshot. And then this is a classical controlled oscillation that is happening by feedback loop due to incorrect controller values. So I jumped into the code and adjusted the PID controller values slightly. What I did is I strengthened the offset value and doubled it, I think, and reduced the integral part by a factor of 10. And I think I also strengthened the derivative component. So essentially going in the direction that the integral part was just too dominant and I needed to strengthen the others. And this happened around, I think this time here, I think it was going down. And this is when I did this, or maybe here. Yeah, there's a small gap, as you can see. And once I did this, this is what happened. So the overshoot wasn't as big. And then it was an oscillation that died down and funneled into this, which is with the target temperature of 27, settling at 26.8 degrees centigrade, which is, in my opinion, quite well. And then I tried to put it to another value, which is more the operating temperature that we actually wanted to be, which is 26 degrees. And there it was slightly off. So now maybe the integral part is maybe too small. This is kind of indicated by this part and this part. But if I increase the integral part, of course, then the overshoot will get worse. And how to counter that is by increasing the derivative part. I'm by no means a controller expert, so don't take my word for it. Just, that is my intuition. And I'm actually happy how this works. And this small offset that is now happening is still remaining is more than okay in my opinion. And I will probably leave it like this, never change a running system. So I'm happy. And I'm also happy that my wife now finally, and she was waiting for that, right? So now she can use it and we can actually find out if having this box and having the climatized environment is improving our dough quality or not. And with this, we are now at the end of this video and was again a success story together with ESPHome. So I really, really, really like this system. I like how simple it is to put it together and making it work for you. And if you liked this video and liked what I did here, I would really appreciate if you could smash the thumbs up button and maybe leave a subscribe to see what's coming up next on this channel. Take care of yourself and your family and your friends and everybody around you. And we see each other soonish in the next video. Until then, I'm your Bushi. See you over and out. Bye.